I'm going to present for my thinking in research point. I'm just started in research points that will be presented today. I'm thinking in integration of a software-defined radio with software-defined network toward future wireless networks. I'm proposing some architecture model and some challenges that we will discuss today. Okay. Our agenda, some motivations, then we quick review the background, that SDR and SDN and wireless virtualizations, system model that I am proposing or I am thinking in, and then theory of operation, benefits and challenges and objectives, the problem statement, suggested tools and equipment, then expected outcomes, and final related work. All of us know that we access demand for data over wireless networks. This is the first point of our motivation to delve into this field. Second point is advances in software-oriented solutions, software-defined radio and software-defined network. But software-defined network is motivated for wired network domain, only for wire. But there is extension for it to work in wireless domain. Okay. Another point is the deployment of virtualizations. The wireless virtualizations also is another point that motivated us to work in this area. And development of SDR cloud. All of us know that SDR is equipped with individual equipments, but there is an idea of how to make RF front-end cloud to be connected with the processing domain in cloud computing resources, okay, as we shall see in this presentation. Background, I think all of us, we know about SDR, so that I'll skip that. If anyone to introduce it, I can skip it. Okay. For SDN software-defined network, the problems that SDN is motivated to work in is excessive line rate. We know that line rates and the bandwidth of links has excess demand, heterogeneous of multiple architectures of network, and misconfiguration errors. Well, what I mean by misconfiguration error here, it's when someone can configure its network or wide network domain, there is some configuration errors. This configuration error will cause the system fail down. So we can imagine when the system fail down, it cause some headache to the operator. So this is another issue, and the complex to manage and control the complexity of systems of the network become more complex to manage and control. Early solutions that will manage to decouple or separation some functionalities that network made and decouple it and separate it from the underlying architecture. This through middle boxes. Now, in the early of networking, the firewalls and netting are embedded on the devices. But now we can separate the firewall or net to be a single device. So the early ideas of separation by the middle boxes. In 2007, a PhD graduate student, Martin Casado at Stanford, think in the concept of separation of the coupling data plane from control plane on the network architecture. This concept came from how to conquer the complexity of this network, our network architectures, how we conquer the complexity of functionalities that appear from interactions between these networks and each other. So the concept of that the computer science scientists know is modularity. We can divide the big problem, the complex problem, to some tactable or tackle some tactile problems to be tractable, or can I tackle it? Okay. This came in thinking in networking through two concepts also, abstractions and recursion. The meaning of abstraction here is abstraction of making abstraction layers. Layering scheme, all of us know the layering scheme of the network, TCP/IP layer. So he's also thought in these ideas to make a layering scheme abstraction layer. That for forwarding abstraction, first one is forwarding abstraction. The meaning of forwarding abstraction is that making a layer of devices that will be forward, only forward, not have any intelligence to make the data forward and the port number or the making any computation for routing algorithm. So the forwarding only forward according to some control came from another layer. Okay, this is the abstraction layer for forwarding. Another abstraction layer, distribution. We know that physically the network equipment is restricted. So I have to make this a distribution layer to make a control in distributed clusters or distributed architectures. Okay. The third abstraction layer is specification abstraction layer. The specification abstraction layer came to when the management or we already agreed about modularity. So the manager or operator module will have to plan for the policy of the network, how the network managed. So he is well interested in the management plan, not interested in how to implement it. Okay, interested in both the plan, but implemented is our implementation is the job of another one. So this meaning of specification abstraction layer. The concept second concept is recursion. How thinking in the networking as recursive. We know that the recursive is a base case, and there are recursive cases from base case. The network is meaning of recursive is the network is network of network. We have a simple network between two nodes connected. It's a simple one, the base one. So this base one can be built up from this another network and to connect. So I have a large area, like a LAN, and from LAN we connected MAN, and from MAN we architecture for WAN. So the second concept of recursion came from here. As the SDN decouples control plane, we formed that, and we shall see in the architecture figure in the next slide. The network operating system is the logic controller placed in this operating system. When we decouple that, we have devices like a machine, and this machine will be managed to give me a service. So I need a network operating system to manage such thing. Okay? And another point, another concept in the SDN is network is programmable via application zoning in OS. Routing protocols, routing algorithms, traffic engineering, security policies. All management, all policies that manage the network became applications that run on NOS, network operating system. Okay? This is a 3 view of SDN and how it's worked. The plane view and functional view, layering view, and operational view. The first view is the data plane of forwarding devices and control plane that have SDN controller or SDN network operating system and management plane. The management plane that a network operator have to manage these networks. Network infrastructure, we talked about that network infrastructure. Southbound interface. Southbound interface is an interface between the physical infrastructure and the hypervisor of network operating system. The hypervisor of network operating system is responsible for making virtual instances. We all of us know the virtual machines. We install virtual machine on our desktop. It's the same concept, but when we install virtual machine, we take a slice of virtual interface, but from the system overview, not from the physical interview. Here is make a slices of network or virtual networks, but from physical interview to network operating system. So the southbound interface, it's implemented as when we can analogous to operating system. It's like a driver. It's like a driver for your system. Okay, that we have a physical machine and install drivers to can use use services that machine more. Okay. So the southbound interface, it has the open flow. By the way, the open flow is the most widely used for network programming or network or SDN, but there is another issues. I refer to the references 3 of SDN architecture to know about modern architectures for southbound interface. OpenFlow is a protocol that installed in open, or can say open vSwitch. Okay, the southbound interface is responsible to interface between network infrastructure and network hypervisor. There are 3 messages from this interface that interact with network infrastructure. It's the first message, event trigger, that any state, any problem with the infrastructure or the physical domain can trigger the network operating system about this problem. Second one, the statistics about what occurring underlying the architecture. And third one, the packet end, or any control message that I need to send to network hypervisor. The network hypervisor is responsible to architect the virtual machines or virtual networks. Okay. Network operating system, as we see, is the management. Manage the virtual machines to meet the control action or control logic, the heart of SDN in this layer, and is implemented in SDN controller. Northbound interface is here for open for developers who want to develop a new routing protocol, new routing algorithm, new traffic policy, new security implementation for this network. It's implemented through northbound interface. It's API. Okay. And language-based virtualization, it's for general, but it's replaced for southbound interface for virtualization issues, but virtualization for software, not for equipment, hardware equipment. Okay. Programming language that used for network operating systems is Pyretic Frontic. A lot of programming language that used for network operating system, and finally, up is the network applications that run it. If you take it analogous to operating system and the kernel, operating system is the lobes kernel, and surrounded by the operating system management, and for management there is APIs for your applications that running on this computer. Something like that you can imagine the operation of SDN. Okay.
Is there a standard already for SDN? Like,
Yeah.
And so if one...
But in each layer, there are a lot of details that refer this reference if you need more details.
So, like, for example, if one node uses a different routing protocol versus the other one.
Yeah.
You talked about routing.
Yeah, so routing protocol, routing algorithm is a network applications.
Sure, but
so to reconfigure it or to design it, you have to work in this for this one.
Sure. If that changes from one software-defined node to the other software-defined node, wherever this...
Sorry? For software-defined network to another software-defined network?
Where is this running? Where is this algorithm or whatever, this whole plane? Is this at the base station?
No, the whole plane is, you have SDN controller, okay?
Yeah.
You configure the routing algorithm what you need.
Correct.
For an instant or for virtual machine that you, for virtual networks that you run your application on it.
Correct.
Okay? Northbound interface takes these actions through operating systems that manage it and forward it to the OpenFlow switch. OpenFlow. This OpenFlow makes the actions and control it to network infrastructure. Like the sending data from computer, you running application, but the data take from up to down to be sent to another time. Okay. Third concept is wireless virtualization. Wireless virtualization also came from the idea of desktop virtualization or server virtualizations. Okay, it's evolved through desktop virtualization, server virtualizations, to network virtualization by SDN, and finally wireless virtualization to integrate the SDN solution with wireless access network. Okay, there are 3 perspectives for wireless virtualizations. The first one is flow-oriented, and second one is protocol-oriented, and third one is spectrum-oriented. That we will focus in our research problem. The flow-oriented, it visualizes the resources of wireless network according to differentiated service of traffic models. That each traffic profile have a service level agreement that we abbreviated by SLA, SLA. This SLA distinguish between each traffic flow. So I can visualize the network resources according to these services for each flow. Another one is protocol-oriented. Protocol-oriented, I visualize the resources according to the operation of protocol itself. Any protocol or any computer protocol or any communication protocol, we can divide it to functional or decision domain and the processing domain. The protocol make actions or control and make processing. So these they distinguish to make the visualization according to that. The third one is spectrum-oriented. Spectrum-oriented, the visualization of spectrum is made according to spectrum. It's motivated by spectrum visualization layer. This spectrum, I have a space and I make some slice of spectrum to be processed, as we will see in details next slide. SV is abbreviation of spectrum visualization. It's multiple examples for open road and virtual LTE, open roads and open radio and so on. Open roads and open radio developed as test bed in Stanford. The scenarios of virtual or wireless virtualization. There are multiple scenarios, but we're interested in the last one. This is spectrum visualization. The scenario is spectrum visualization. Okay. Challenge with virtual wireless visualizations is a flexibility performance trade-off. It's a challenge. It's a general challenge for software-oriented solutions. The goal of any software-oriented solution is to achieve flexibility, to have a flexible solution to reconfigure the devices, to reconfigure the protocol, to evolve, to have to save time, to save cost. But the cost of this flexibility is performance in terms of throughput, overall throughput of application, latency, the quality of service levels, maybe security. So there are a lot of flexibility performance trade-off is a main concern in working in wireless virtualization. Okay. Scalability, it's an important challenge also in wireless virtualization. Extensibility and ease of implementation. If this wireless virtualization scheme is extendable, can be extended, and what is the complexity of implementation? It's complex or can be visible to be designed. Sorry. Requirement. Still, wireless virtualization needs generic and middle external interface to implement it. Evolve a framework. There is not a general framework for wireless virtualization. And the third one, isolation for resources and abstractions for the services, as we hear in the SDN. Okay. Really, the idea of my research point came from this architecture. It's proposed in the refers to this reference. It's here how to integrate the three solutions for wireless virtualizations, network virtualizations, host virtualization, and deliver or provide network as a service. We need in cloud computing, there is infrastructure as a service. The same concept exists here, how to make infrastructure slices to be a virtual provider, a virtual network provider. So it's how to integrate wireless virtualization with network virtualization and the host virtualization that's that are implemented already with cloud computing solutions, and this implemented with SDN solutions, and this is the issue in ongoing research. Here, it's a system model that I'm thinking in or I am proposing for the SDR, SDN integration. Here we decoupled the RF ends. Okay, the RF ends decoupled, and the most of signal processing of SDR module is moved to the cloud resource. We know the cloud is have GBP units, but it has to give a computational power, high computational power, that does not exist in modular or individual slides. Okay, there is another layer here before processing or integrated with such a cloud processing is a spectrum virtualization layer. Spectrum virtualization layer, the idea of a spectrum virtualization layer, how to have a spectrum space and get a slices of frequency. Say we have, I need a physical carrier, a signal carrier here, frequency carrier here, in a certain band, and it's not available in spectrum space. But there is another carrier is available. So what occurs here? Occurs the reshaping. The SVL is based on reshaping. There is a reshaping of signals. What's the meaning of reshaping? It's modulate to another carrier. Modulate this signal to another carrier that is already available. Okay? This is the spectrum virtualization layer. And the cloud computing that has SDR processing. There's a problem here. It's a spectrum manager and the spectrum map. How to map spectrum, the idle spectrum to the required spectrum. And how this is running in real time. Okay? Now, how do SDN controller control that and control with the architecture of SDN that proposed in the first? SDN controller already has the traffic profiles of upper layers or our applications. So these traffic profiles, how can integrate it with the cloud computing that running the process of signal processing? And how to manipulate and manage the spectrum that's running here. Okay. This SDN controller, it's implemented in southbound. This suggested domains that will be integrated with cloud computing here. Sorry, with SDR. There are two problems here. Main problems are resource computing resource allocations. We know that cloud computing is shared among a lot. So among a lot applications and among a lot of providers, who need the service. How to allocate the resources of computing here and how to allocate the resources for spectrum manager. Still, for spectrum virtualization, still there is a problem with spectrum manager. How to allocate this? Okay. By the way, there is resource space and SVL spectrum virtualization layer, physical layer, and this virtual wireless access instance or slices of virtual access. It includes the physical and MAC.
So are you saying that the spectrum virtualization is decoupled from Phi and MAC?
Yes, decoupled. It's already implemented for in the reference that we will in a related work. It's already implemented SDR cloud. So SDR cloud, but the integration with spectrum virtualization layer it's a challenge one. But the SDR cloud is already implemented. That SDR running cloud computing running the signal processing for the RF cloud field.
Right. Because I mean, one would expect that if your antennas, you have a wired connection to everything in the network, you can sort of do a centralized optimization,
it's
right?
It's not connected. It's connected to cloud computing. It's an optical backhaul.
So these are optical fibers that are going to all the antennas.
Yes, optical fiber.
And they are all coming back to the cloud.
Yeah.
And one would expect if you were able to somehow manage all those antennas jointly, that is what we call centralized optimization of this problem.
Yeah.
Somehow you would try to do a joint optimization of your whole system
Mhm.
But if you decouple, then you are losing some information of, you could have a better performance if you did all these, whatever you are decoupling together. So that's where the performance loss is there, and probably you also alluded to that
Yeah.
in one of the earlier slides.
This serial of operation. The SD controller addresses the quality of service requirement for each traffic flow. It's already implemented for SDN controller. Okay. This traffic or this requirements code is mapped to the SDR cloud to update the spectrum map. Spectrum map is a data structure that is well implemented in the cloud. Okay. According to physical channel status. Physical channel status that is received from the far field or cloud of RF front end. Okay. SDR cloud manage dynamically the computing resources. That's the challenging one. It's the two modules here are challenging. And last is SDR cloud update SDN controller with spectrum status that can switch to make another slide in which a traffic profile can pick up a virtual slice or virtual network slice. Okay. The benefits, a lot of benefits of this architecture model. We hope to achieve the main objectives of fifth generation, support massive number symplectic connection device, and the high system spectral efficiency, low latency, high versatility. The low latency, clearly it's a challenge with latency. That latency for how to allocate the resources for real-time processing. Unified management for wired and wireless network, unified policy enforcement, network programmability, and to introduce the network as a service, performance improvement, and vendor interoperability.
So what are the latency requirements of 5G?
Latency, it's the latest delay. I can minimize the latency. I need to minimize the latency and delay.
Right, but what are the suggested requirements for 5G? Do we have any information about that already?
No.
Suggested numbers? So you're saying that everything is happening in the cloud, right? So where is this cloud located?
The cloud?
These are somebody else computers which are located, as Dr. McKenzie said in his talk. This cloud is basically somebody else's computer.
Not computer. It's a cloud computing provided by operator of cloud.
But in this case, so when you think about the cloud, it's physically located. It could be distributed across a country, and with those latency goals in mind, you still have to physically.
No, I'm not distributed now. It's physically located in a central place. Distributed as well.
But so is that going to be co-located with your antennas, or is that going to be? So, for example.
No, the antennas is distributed along a large geographical area, so it's connected with optical fiber to make a high-speed connection between antenna speeds that distributed geographical area. It's not sense to locate the front feed with cloud.
So you have a centralized processing unit that is sitting geographically closer to those antennas.
Yeah.
Right. Okay, and that's what you're calling cloud.
Yeah.
Then what is the problem? So then why not do centralized?
Exactly. That's what. If you have that setup where you have a few antennas being controlled by a centralized processing unit, why not to do a complete centralized optimization of the system? Maybe we are just oversimplifying, but that is possible because you will at the end be maybe connected to 10 cells, and optimizing centrally over 10 cells is not really a huge deal.
Unless you can show like drastic, some sort of drastic gain for distribution.
Unless you are scaling up and you really have a true meaning of cloud where you are controlling a large geographical area, but then your latency will come into picture. Latency problems will come into picture. So you are limited by latency, which means you have to really limit and locate your cloud somewhere closer to the antennas. If you are limited in the region, then why not just do the centralized
But if it's limited, to a region, I think it's not make sense to as analyzer. There are other alternatives that it's cloud radio access network.
Yes.
So
You have a CRAN, yes.
Yeah, CRAN that. So I needed to make this solution. It's so close to this area.
That's right, but then the latency will be a problem, as Dan said. I mean, you will have these processing units far away, right? And so at least you'll have to send that data over optical fibers to those computers. That needs time, and then the solution has to come back. That will need time.
Mm-hmm.
And looking at the 5G latencies, which obviously will be lower than 4G, that may not be possible.
I remember saying that you are trying to optimize over individual flows, like your SDN or whatever.
Yeah,
the
whole
is
SDN is
optimizing over individual flows. I think that's contradictory to that fact, right? If you are doing CRAN, I don't think optimizing over a flow is an option. I mean, a flow is created for like on a very small time scale.
So overall, the architecture is, at least to me, it's not very clear at the moment.
The challenge for this architecture is there are three basic challenges: cloud resource management, as we see, and system performance. And the third is the third challenge is security challenge. It's out of my scope. I didn't explore in the security issues related to such, but it's a problem with cloud resources for SDR that I need a very fast response time to my signal processing. So I have to optimize these resources, so response time, and also for SDR. On the other hand, for SDN message control message that will interchange between SDR cloud and SDN. Second one is system performance. That is for next phase. I need to measure performance of system and to prove if it is program or complex, and may evaluate the flexibility performance trade-off, and evaluate the power consumption. Okay, for security, it's open issue. How SDR threats move to the cloud, and how SDN threats will interact with these dark cloud resources. It's open issue that there are already papers of moving target defense related for SDN, SDR integration. So our objective is to maximize the resource utilization constraint with minimum response and execution time for computing resources and spectrum resources, and minimize power consumption, and improve end-to-end quality of service. The SDN controllers that working in both wired and wireless, so I need to improve the end-to-end quality of service requirement in terms of throughput and end-to-end delay measurement. Also evaluate the flexibility performance trade-off. I divide the problem statement into two phases. First phase is an analytical, that I need to optimize the resources as that I said in my objectives, and optimize the power consumption for computing energy resources and communication energy resources I have. Phase two, to evaluate the performance. Evaluate the performance needs some prototyping or some implementation, and using SDN-based cognitive radio management as a performance benchmark. There are needed tools, optimization software that I need to optimize these resources, maybe model, and Mininet for OpenFlow, and LabVIEW for general radio. Equipment that for prototyping, it may need, there are open air interface is test bed for integrating SDR solutions with SDN. And Jenny testbed is also for who interested in research in SDN or research on evolving protocol. Is developed by Stanford who interested in development. Okay. And Open Roads for mobility management, or interested in mobility management evaluation. Expected outcomes, identifying optical requirements for SDR-SDN integration for more. I hope to obtain sample prototype to verify feasibility of this integration, evaluate system performance. there are a lot of related work related to such issue. That first one one is integration of SDR with SDN. This is, to the best of my knowledge, is the first idea to how to integrate SDR with SDN. It claims there is a SDR and SDN relationship in centralized management. It expects that SDR and SDN integration made a quality of service levels. There are some shortcomings here. He proposed the idea, but made any performance evaluation, not any implementation, not any evaluation at all to this idea. So this is the main shortcoming. Second related work is resource management for software-defined radio cloud. Resource management is address the challenge of how to allocate the computing resource for signals that interchange between the far field of antennas field, RF front end, and computing resource that located in SDR cloud. Here it doesn't consider personalized scheme. It considers only the signal processing for signals that came from far field and the signals response. The deployment of massive management SDR cloud computing and the limits is extension for the first work of SDR cloud. SORA is a high-performance software. SORA is a software radio, but it's implemented in GPP, general purpose processor. It's how to virtualize the operation, but operation of protocols on a software radio. Okay. It is fault flexible to provide the field, but it's hard to program. The problem is it's hard to implement. Unable flexible spectrum is the idea of dynamic spectrum or flexible spectrum access that for spectrum visualizations. The main contribution here was to reshaping the signal, to map the signal from a specific band to another band. The main contribution here, but it wasn't interested in resource management for spectrum map, how to update the spectrum map and spectrum management. Picasso is another flexible RF for spectrum visualizations, but it provides flexible for spectrum slicing, but it's designed for FPGA hardware. FPGA hardware is complex to program. Open radio is an alternative SDR solution. In Open Radio, it's a platform also developed by Stanford, and it's provide the flexibility and the performance trade-off, and it decomposes the protocol. So for Open Radio, it decomposes the protocol. It's when we talk at the beginning about the protocol-oriented wireless virtualizations, here it decomposes the protocol to the session domain and processing domain. So the wireless or wireless sources here visualized according to the wireless protocol. He only implemented this prototype on the Wi-Fi MAC protocol. SoftRAN is software-defined radio in the network. Is also a controller is moved to the cloud, and this is antennas or base station in the farm field. This antennas there is connected, so software or base station API. There are controllers. This signals here, it's send projected signal status, or channel status first channel is updated periodically to the controllers which have the signal processing of video signals. It's a neglects link delay between base station's field and the controller. It's the state which the backward that will have the signals and intershare with this controller. SoftRAN the controller is placed integrated with SDN, or proposed for that. HCCRAN, Heterogeneous Cloud Radio Access Network, is large work here, but here is defined as three levels of visualizations: spectrum visualization for spectrum size, and infrastructure visualization and network visualization. Here, infrastructure virtualizations based on baseband units and remote radio host. Okay? Remote radio is connected with baseband unit that have the computational capability for the signals that collected from radio RRH. This is another kind of wireless infrastructure virtualization for HDD. But here it's a heterogeneity, it's mis-heterogeneity, it's assume heterogeneity for cell size. It's use the same technology. Okay. And final one is it's a software-defined cognitive radio network. There is a lot of work, but it neglects the spectrum sensing time.
That you have talked about, whatever you have talked about now, what is the area that they have considered for their implementation?
The area?
Yeah, I mean, you said they are all implemented in Stanford testbed or whatever. You
No,
said they are all implemented.
I'm not implemented, but I can go test bed that already implemented and apply it.
Okay, so do we have any questions about Imad's presentation?
Come on, we have so many SDRs.
Oh, so I've got one. If you look at some of what you've been sort of proposing as where the cloud or where your processing is done, you had mentioned these are all going to be sort of centrally located. Will one processing unit always be dedicated to certain radio heads? And will those compute units be able to talk with, for example, radio heads that are located, geographically nearby?
No. You mean it's one only source, one only computing dedicated for the radio head?
Mm-hmm. Well, so you mentioned typically your cloud is really a data center that just
and there
yeah.
is what's mean the resource allocator.
Yes, and
the resource allocator is it maps the signals updates to the SDR.
So in this case, in some cases, like let's say that you have interference between cells, as part of your radio management, will the data centers be able to talk to each other for neighboring antennas that aren't controlled by a single data center?
It is controlled by it, but it's through SVL, spectrum visualizations, that has a spectrum management module and a spectrum that solves the problem of interference.
Okay, thank you. All right, going once.
I have a small question about the SVN. So I think you mentioned in response to one of Dr. Dhiren's questions that your SVN is decoupled from the PHY and MAC layers.
Yeah.
I did not really understand how then the SVN works, and you said it will take care of interference. The only way I can think about it is if you are talking at a flow level, which is like an end-to-end pipe.
Yeah.
But if it's completely decoupled from the PHY and MAC layers, how does it solve the interference problems? Like, how does it do the resource allocation? What do you mean by a virtual spectrum?
The SVL contains a reshaper and spectrum map and spectrum manager module. Okay, it's also implemented in software. By the way, it's SVL implemented over SWAP. Okay, not a hardware solution, software functions, it's software.
Sure. So I'm saying if it's decoupled from the PHY layer, how does the spectrum management module work?
Yeah, it's a coupled coupling here the signals is shape and needs the spectrum. How for the MAC? We talk about the MAC layer.
Yeah. So, okay, I guess